Hey, I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast that helps you understand the chemistry of your everyday life.
You almost took my line, Jam.
Wait, what?
You opened your mouth on the and welcome to Chemistry for Your Life part.
Well, you paused unusually long. I was like, does she want me to do that?
No, it's my, don't be a line usurper.
I think that's a really catchy phrase you've come up with for what that is. I think it's going to catch on.
Thank you. Line usurper. Okay. Are you ready to get started?
Let's do it.
Do you want to know what you're going to learn about today?
Oh, yeah. I guess I'd like to do that first before I commit to anything.
Yeah.
So, yeah.
Have you ever seen a gecko?
Oh, yeah. I've seen lots of geckos in my lifetime.
Where have you seen them?
Well, I guess I don't know what exactly breed of lizard it is or whatever, but I'm pretty sure they're geckos. Mm-hmm. And they like to hang out on front and back porches of the houses that I've lived in.
Yep. I remember.
Oh, yeah. Many of them.
Yeah. When I was a little kid, we saw my grandma. She has this big window that she never had curtains on or closed or anything. And we would just watch the geckos crawl around on the window.
Yeah. It's pretty normal for us to like say it's already nighttime and I'll walk out of our front door to go get something out of my car, something like that. I'll flip on the light for our porch and then walk out, and all that sudden change, all these geckos just go. It's like you just see like out of the corner of your eye all these little tiny shapes like scurry away.
Yeah. So have you ever thought about, I don't know, how they hold onto the walls and walk around?
You know, I have not thought about that probably since I was a kid. Like, I'm sure something as a kid that I was like, what the heck? How are they breaking all the rules doing this? But I'm just so used to it now, and I've seen so many of them so much at the time. So I have not thought about that in a while.
You've lost your little scientist inside you.
Yeah.
I like to say that all children are little scientists because they all have this sense of curiosity and asking questions, and we can either foster that or squash it out. You've squashed out your little scientist.
Or maybe my little scientist just got like numb from not knowing. It's like all this curiosity that went Can I use the phrase unrequited in the situation?
Sure.
Unrequited curiosity. It just never got answers to that little scientist, and they're just like, oh man, I guess the world's just dumb and boring, and it's all it's ever gonna be.
Well, I'm here to undumb and boring it for you. I'm gonna liven the world up for your little scientist inside you.
Perfect.
For the little kid inside of you.
Okay.
So, do you want to know how geckos walk on the walls?
Yes, I do. How do they do it?
Are you ready?
I think so.
Oh, do you want to guess?
Okay. I can definitely try to guess.
Try. Don't look at my notes.
Okay, I'm not looking at your notes. One thought that comes to mind is thinking about how in SpiderMan 1, the Tobey Maguire one that came out in like 2000 something, he has these like, it shows like a really close-up shot of whenever after he gets bit by the spider and he first discovers he can crawl on the walls. He has these tiny little like fiber things sticking out of his fingers.
That is good. But what is it about those fibers?
Well, he has those, and then because of that, I guess it can like increase friction enough because there's a lot of them. I don't know, really. They don't explain that part, obviously, because they're just showing a movie. But he starts then putting his hand on the wall, and then it's like it stays with these little things with the brick walls or something like that. So he does that, and it works. And so that's my only theory, because I don't think that they're I don't think they have some sort of glue. Maybe like 5-year-old me would have thought that. But it seems like it could be likely that they based SpiderMan they based geckos on SpiderMan.
Oh yeah, definitely. SpiderMan came first.
And so maybe there's something like that. That's my only idea.
Okay, so that's a really actually good idea. Actually, that's pretty smart.
Okay.
I'm going to give you the brief, and then we're going to go in depth.
Oh, sweet. Okay, cool.
So this is stickiness part 2.
Oh, nice.
The gecko story.
Dang.
We talked about how everything in the world that is stuck to another thing is usually as a result of
intermolecular forces.
That's right. Ding, 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 ding. And geckos are no different. Geckos walk on walls from intermolecular forces.
Dang. Wow.
But
so they have the force.
The forces with geckos.
Yeah.
Absolutely.
Got it. Okay, cool.
May the intermolecular forces be with the geckos.
Man, there's so much more than meets the eye with the geckos.
There is.
You know?
You're at a cocktail party with some friends. You're trying to impress them. You say, did you know how geckos climb on walls?
Mm-hmm.
It's intermolecular forces.
But if at this party, which I can't envision myself at because it sounds like fancy and stuff, wouldn't the people around me be like, oh yeah? Well, how?
Maybe so. And that's what we're going to talk about next.
Okay, so I got to remember a lot in order to make an impression at this party.
Well, hopefully you already remember a lot from all the other episodes you've listened to before. So you could pull out your microwave business if you want.
That's
or
true. The
your
microwave
pot
thing,
boiling business.
the microwave thing is a great like party story kind of thing.
Yeah.
Because everybody wonders it. I mean, even if they feel like a little bit too dumb to mention it, it's like, okay, I still don't understand microwaves. Everybody's got that.
So intermolecular forces are responsible for geckos being able to walk on walls. However, what kind of intermolecular forces is the question? And how do they allow geckos to walk on walls? So we talked about one kind of intermolecular forces, the strongest kind, last week.
Hydrogen
Bonding.
Yes.
Yes. So hydrogen bonding is what we talked about last week. And this week we're going to talk about the weakest intermolecular force. Dispersion forces.
How is it the weakest one? Like what makes it less strong than the hydrogen bonding?
That's a good question, Jam. So do you remember last week we talked about how magnets have poles and we used that as an analogy for dipole in molecules?
Yes, I do. Yeah.
There's a negative on one side, there's a positive on the other. Well, in some molecules that's built into the molecule.
Right.
It's permanently like that.
Yeah, like the same thing is true with the hydrogen bonding, right? It's like totally built in. Totally built in,
permanent, and very strong.
Yeah.
In some other polar molecules, like we talked about with soap, it's less strong but still built in. What we haven't talked about yet is dispersion forces, which are those weak forces. So dispersion forces, what makes them so weak is that polarity is instantaneous and then it goes away.
Okay.
So we talk about it being an induced polarity in science. So do you ever remember, this is the best way I can think about it. Did you ever have one of those things when you were a little kid that if you dragged a pin along a glass, whatever, you would see those little magnetic shavings move with it?
Yes, yeah.
And then if you took the pin away, it would go away?
Yeah.
It would just fall down?
Yeah, well actually, I thought for some reason you had to shake it to get that to happen.
I think I might be thinking of something at a museum then instead.
Oh, okay.
But if you can have something that it's temporarily going to stick, and then when you take the thing that's causing it to stick away, it won't be that way anymore.
Got it, yes.
So dispersion forces are like that.
Okay.
Dispersion forces, if they come into contact with another molecule, because two negative charges don't want to be near each other, two positive charges won't be near each other, they will momentarily create one will be negative and one will be positive. It'll be a momentary dipole and then it'll go away.
Okay.
Do you got that?
Yes, I do.
Can you say it back for me and the listeners?
So basically, the other types of intermolecular forces that are stronger are kind of built into the structure in some way.
Yes.
For whatever reason, which I guess we'll get into a little bit more, but in this case, they are not built into the structure. They're able to be induced by something that causes there to be that force temporarily.
Yes.
Like the temporary magnet thing.
Exactly.
Which makes sense. That illustration is helpful because it is like, oh yeah, that's easy. Like you take the the magnetic thing away, and the thing's gonna fall. It's like makes a lot of sense.
Yes, that's it. That's exactly right.
Okay,
you got it. So they're induced basically by being near each other.
Okay,
that's a thing that causes the induced dipole, is just coming close to another electron cloud. They'll both polarize to where the negatives are opposite sides and the positives are on opposite sides. So they're touching each other.
Interesting.
And it's hard to explain. That's why I saved it for last.
Yeah.
In our intermolecular forces exploration. So that is the basics of dispersion. Really, that's all of dispersion forces.
Yeah.
So does that make sense to you?
It does actually. Yeah, I'm surprised kind of that it does.
Why are you surprised? You're good at learning.
It just sounded, and right off the bat, it sounded like it was going to be more complicated to like even get a little bit of a foothold in. The other ones are built into the structure. This one's like, it's temporary. And it's like, okay, that seems like it's the area that's going to have the most exceptions. Like there's so many things where it's like, here's a clear cut thing, here's a clear cut thing, and then here's the exceptions category. Here's where all the crazy stuff happens that we had to lump into a category. And so I kind of maybe thought that it was going to be more like that.
Well, you did it. You got it.
Whoa.
Congratulations.
So the geckos are magnets? I'm just kidding.
No, they kind of can do that. So now we'll get into geckos. So
okay.
You know the overview. We talked about how do geckos stick on walls. Mm-hmm. Well, they use dispersion forces. Dispersions are the temporary induced weak intermolecular forces.
Okay.
So how do they use those relatively weak intermolecular forces to hang on walls? Well, I'll tell you. They use a bunch of them.
Uh-huh.
So you talked about how SpiderMan has those little tiny, almost hair-like things on his fingers.
Uh-huh.
Geckos have that. They have, now let me look to make sure I get the word right. So they have lots of, we're talking hundreds of thousands of teeny tiny hairs on them.
Uh-huh.
And each one of those hairs is also branching up into a bunch of hairs. The thing it made me think of was when you have split ends.
Okay.
And you have your one strand of hair, and then sometimes it'll split, and then that split will split, and it will have all these teeny tiny hairs coming off of it.
Yeah.
That is what geckos have.
Okay.
So they have teeny tiny hairs, and each one has, I'm sure this is at the microscopic level, a flat triangular tip.
Uh-huh.
They actually call those, I think it's pronounced spatulae, but it's basically little spatulas. Uh-huh. And so because there are so many of those tiny spatulae on the gecko's feet, there's a huge surface area, and all over that surface area, there is the possibility for weak intermolecular forces.
Yeah.
And so they use that where they can curl or uncurl their toes. And when they're changing the way their toes are, they can induce that dipole and use it to stick on the wall.
Wow. That is crazy.
Isn't that amazing?
Yeah, that's nuts.
I could not believe it. And I want to give a shout out. I'll do some references at the end. But I had no idea this was true until I listened to a podcast called Ologies, and there was an interview with a graduate student who studies geckos.
Okay.
Or all lizards, maybe.
Yeah.
And they started talking about these intermolecular forces, and I was so excited. And then I went and did more research, and actually there's information about this in every organic chemistry book that I've been looking at. I had no idea.
Wow, that's crazy.
Yeah, so I thought that was so exciting.
So each of the so they got the hair thing that comes off, that then splits into a lot more hairs, and then has a spatula at the end. And so...
Has a spatula, just call it a spatula. That's sorry, biologists, but it's a spatula now.
And because each of those little spatulas create that dispersion force.
When the gecko knows how to basically move its foot to induce the charge.
To induce it. So each of those make a little bit of that charge. And then because there's so many of those little hairs and spatulas, it all adds up to be enough to hold their weight.
Yes. And
That's
to hold
crazy.
their weight onto the surface.
Yeah. That's pretty crazy because it's like, it seems like just one would be almost nothing, right? One little hair and thing like that would not be enough to hold anything on there. Yeah. But it's like, if you can just pack them in there, they all add up enough.
Yes.
Which is, it's fascinating. I'm sure there's a lot of like engineers who are like, oh no, that's how it works. Like any structure you build is a lot of things.
Little things adding
up to be a strong structure. But to me, I don't know anything about that. And so it's like amazing that there's like these little hairs that can do that just because they have strength in numbers kind of deal.
Right. It's pretty incredible. And it's incredible to me that also that's developed, and then that the geckos know how to use it. And because they can pick up their foots don't feel, and this goes back to last week, their foots don't feel sticky when you touch them, but they know how to turn their toes to get it to where they're going to stick on, and they're suddenly, quote, sticky.
I wonder what would it feel like to have a gecko do that on your hand, like actually engage it, like be held upside down. Maybe it wouldn't feel that weird, but like,
I don't know.
now I'm wondering. I mean, I think I probably have held a gecko, but I don't think I ever had it like try to like stick to me. You know what I mean? I wouldn't. I don't think I've experienced that.
Well, I want to say one more thing.
Okay.
And this to me is really impressive. So, do you want to know how the scientists figured out that it's dispersion forces and not one of the other ones?
Yes.
So this is going a little deeper into the science.
Uh-huh.
So if you're just happy knowing, to the listeners out there, if you're just happy knowing it's dispersion forces and that's that, that's fine. But the way they figured it out is they tested to see how well geckos stuck on both a polar surface and a non-polar surface.
Okay.
So remember polarity, that's where it's built in the negative and positive into the molecule. And non-polar, the electrons are equally shared. There's no positive or negative. And the geckos could stick on a non-polar surface as equally well as they could stick to a polar surface.
Whoa.
Which means their feet had to be inducing the positive or negative, and it wasn't a built-in positive or negative on their feet.
Got it. Okay. Yeah. That makes sense. So like, if it wasn't their feet, then there would have been a clear difference between the surfaces, right? Like they would have just been not been able to stick to one of them.
Yes.
Okay.
They could have even been repulsed by one. If the positive charge was the one that was out and then they came to the positive side of a surface, maybe they'd be repulsed. Yeah. Or if it lined up right, they could maybe easily climb up a polar surface, but not a non-polar surface.
Yeah.
But geckos can climb up any surface equally well, which means that they are inducing the charge on the tips of their feet without regard to what the surface they're climbing up on. They can induce a pull in their feet that climbs up on the surface no matter what.
Oh my gosh. We've got to figure out how to get this to humans.
Isn't that amazing?
We've got to learn how to do this kind of climbing deal.
And I do want to shout out the scientists who did this because I think it's really cool. It said it was Keller Autumn who leads a multi-institutional gecko research team.
Wow.
And this research was done in 2000. And I want to give my references at the end, but I just wanted to give a shout out. Scientists are doing such cool work. Yeah. And that was in 2000.
Yeah.
So.
Man, that's crazy.
So cool, right?
Yeah, that really is cool. And like, I love that the little scientist inside of that team was like still alive. You know what I mean? They're like, listen, we've been wondering ever since we were all 5 years old how geckos do it. Yeah. Let's get together. Let's figure this out. Okay.
Well, and I think that they're going to be able to use that in engineering and technology, whatever, the people who develop that stuff to develop better adhesives and other good applications.
Wow. Yeah.
Like SpiderMan's gloves.
Yes, exactly.
Oh, what is his hands though? Not his gloves.
It's his hands, yeah.
But he wears gloves over his hands.
Yeah, so it still works through them somehow.
So it's probably on the gloves. Maybe he's inducing a dipole through the gloves.
Through it, yeah. Yeah.
So they could make real life Spider-Man gloves that hold us when we climb up.
That'd be awesome. Seriously, that'd be so cool.
It would be awesome.
Gosh.
Okay, so that's it.
Wow.
Now you know how geckos climb up walls and glass and everything else.
Dang, those sneaky geckos.
Sneaky geckos.
They've been these little chemists this whole time, crawling all over our porches and our eaves and stuff.
They've been little Spider-Men using their science magic.
Also, shout out to Spider-Man 1. Sam Raimi, I believe, directed that one. Tobey Maguire, looking at you.
Yeah, I don't know anything about those people that you just said, but I do like Tobey Maguire, so good stuff. So now it's your turn. Will you teach me about how geckos climb up walls, Jam?
I'll be happy to. So, just like we saw in the 2002 movie Spider-Man, life-changing movie.
For some reason, I thought you were going to say in 2000. Is it 2001: A Space Odyssey?
Oh yeah, that's a really good movie. I can't find a way to reference that one in this situation.
I really thought that's what was about to come out of your mouth. I have no idea why.
That is probably my most referenced movie in my life. I'm like, well, just like in 2001: Space Odyssey. Some people haven't seen it too. That I really probably could reference anything.
I've not seen it
and say that movie, and people would think like, wow, that's a crazy movie. Like, how many different crazy scenes and eras are there? Okay, so in the life-changing 2002 movie Spider-Man by Sam Raimi, we see Spider-Man have these little hairs on his fingers.
On his fingies.
On his fingies. And just like Spider-Man, geckos have that. So that the little hair splits into more hairs and then has spatulas at the end. At the end of all of that, they're able to, in some way, they know how to do it consciously, create the type of intermolecular force that's called dispersion force, which creates a temporary polar dipole force between the gecko's hairs on its hands and whatever surface they're trying to walk on. And because of that, it can be any surface.
Yeah.
It doesn't have to be some perfect material that works well with that. They're creating that intermolecular force just because they're in control of it with the hairs and stuff on their hands.
Yeah.
And then that's how they are the top of the food chain.
And it is the cumulative effect of all of those little spatulas that do it. I think you had said that earlier, but I just want to make sure. So that's how even weak intermolecular forces help the world go around and do really cool things.
Yeah. Gosh, that's so crazy.
Isn't it amazing?
I wish I could kind of see like this. I mean, I feel like there's probably something out there like this, but some like it had to be CGI, but like zoomed in kind of thing of what that would look like if we could see it. Where like the gecko like opens its hand and then you see all the little hairs come out and then like kind of see like a little bit of they'd have to make it visible because it's probably pretty invisible.
Right.
But seeing it and then go onto the wall, that'd be so cool to watch.
That would be.
You know?
Yeah. So if there's any really skilled graphic animators out there that want to use their skills to make a brief design of, of how gecko's feet work, we would think that was beautiful. We could not pay you, but we would definitely retweet and share it on Instagram.
Yeah. Or you know what? If we could work it into, I think if Pixar could find some way to need to like work that into a movie they're already developing. So, you know, in Coco 2, if you guys do that, add a lizard in there, a gecko specifically, and then do a really detailed animation about how it sticks to the wall. Just include it in there so that budget-wise, it kind of makes a little more sense.
Perfect.
So
love it. Okay, so we're going to go into our references. I just wanted to, and I think I'm going to start doing this. I stole this idea from another podcast that Emily told me about. Where I just put all my references at the end. And a lot of times it'll just either be stuff I learned in class or my textbooks, but I'll even share the references of what I use to double check what I've learned.
Okay. That sounds great. Especially because like there's probably some people who would be at the ready interested in like exploring those references themselves if they're that interested. So it's kind of cool to give that ability to people.
Well, and that, yeah. So if you want to, you can check these out. So the first one you may not have access to, but it's the 11th edition of the Solomon's Organic Textbook, and we've put pictures of that on the Instagram before. And then I also used a textbook available on OpenStax, mostly because I don't have a PDF of a Gen Chem textbook. And this OpenStax one is available on my computer. So the book is called Chemistry. It's the second edition, and the authors are Paul Flowers, Klaus Theopold, hope I said your name right, Klaus, Richard Langley, and William R. Robinson.
Whoa, I wonder if I'm related to him.
So,
William, oh, sorry.
Are you related to him?
No, I was thinking Will Robinson's like Will Robinson from Lost in Space.
Not seen that either, but those are our senior contributing authors to this OpenStax textbook that is available online. And the last source I used was the episode of Ologies called Serology, which is the ology of lizards. And she interviewed, that's Allie Ward. She has a podcast about where she just interviews scientists. And she interviewed Erin McGee, who is a lizard scientist. I believe she was a grad student. So go check out that episode because it was really cool. Those are the sources I used to put together this episode of Chemistry for Your Life.
Awesome. Dang.
Now, before we sign out, I want to hear about what was one thing that made you happy this week.
Okay, this one's a simple one. It's not as cool as previous ones, but a very small thing that just brought me a little bit of joy this week is that they came out with a version of Mario Kart for phones. I think it's on Android and iPhone and whatever else. And I just haven't played the game in so long. And the one I played the most was like the super old Nintendo 64 one. It wasn't the first one, but that was like one of the really popular ones. And so I've been playing that little app game. And I'm not even like a game on my phone kind of person.
No, you're not.
But there's just the joy of like, oh yeah, remember how fun this game was? It's so simple. It's just you're in these little carts going around tracks, whatever. But it's just like all those fun memories about having played that for hours when I was a kid. So that's made me a little bit happy this week, thinking about simpler times.
Nostalgia. I think that's why Pokemon Go is so popular.
It probably is.
I was like, we're back in our childhood. I would lose it if a Pokemon game, like they had the Game Boy Color, red, blue, crystal version. If I could play that on my phone.
Yeah.
Just an app that was like cheap and easy to download. I didn't have to do anything crazy.
Yeah.
I would love that. I would absolutely spend so much time playing that.
Yeah, I think they could easily do that. I mean, those games, like if you ever look at just the size of like a Game Boy game, it's kind of amazing stuff, but they'll be like, oh yeah, this Game Boy game that you spent hours on was about this many megabytes of data. It's
you could put that on a phone.
You could put that on a phone so fast.
Oh, and I would love it. If it looked the same and had the same noises, I would be so happy.
Yeah. Yeah.
And I had kept my Game Boy Color until college, and then I let someone borrow it, and they never gave it back.
Oh, no.
Brutal.
Shout out to that person?
No, I won't.
Okay.
But I'm mad about it.
Just, you know who you are.
You know who you are. And if you want to give that Game Boy Color back, I would be very, very happy because I'm not willing to go find one.
She could share about it at the end of an episode, just like this.
Oh, absolutely, I would.
So what about you? What made you happy this week?
Well, I've had a pretty good week. School and everything's going well, but I did have some weird, unexpected struggles. I won't go into too much detail. Yeah. It's just, the regular ins and outs of grad school. And I had some friends who were really willing to help me and took some stuff off my plate and just stepped up whenever I was having a really hard time. Yeah. I mean, everything else in my life is really good, but there was this one weird, hard area. And a lot of my friends just stepped up and were really kind when I was open and shared with them that I was having a hard time. And so I think friendship is my happy thing this week, is having, like good friends that you can tell when stuff isn't going well, and they're willing to get in the trenches with you and bear that with you. So you're not all by yourself with this just situation,
Totally. Man, that's awesome.
Yeah.
Yeah, that makes a huge difference.
It does. Trying to do it by yourself is not, it's just not how humans are designed to be, I don't think. So
Agreed.
So that's it. That's this week of Chemistry for Your Life. I want to say thanks to Jam and you guys for listening and learning, but I also want to give a shout out to some of our new and fun countries that we have listeners in this week.
All right.
So we added in Nigeria, and this one's very cool and very small. Cyprus.
Oh, yeah. I know where that is.
Island country.
It's just off of, away from the Holy Land, like right near there.
Yes, we also added listeners in the Holy Land and in Lebanon.
Oh,
so
nice.
We've got lots of people there in what is that, the Mediterranean Sea, and just off of it.
Yeah.
So that's cool and exciting. And we added a listener or two, it's hard to say how many, in New Caledonia.
Whoa.
That's a Pacific Island country.
I mean, that's awesome. I've heard of that place, but don't know almost anything about it.
Yeah, so thank you guys so much for listening in those areas, in those countries. It's really fun to spot them. The little blue dots are adding up, and just to see our listenership grow all around the world is really incredible, and we can never thank you guys enough. So thanks so much for listening and tuning in.
Yeah, it's totally mind-blowing. Thank you all so much. Melissa and I have a lot of ideas for topics of chemistry and everyday life, but we want to hear from you. So if you have questions or ideas, you can reach out to us on Gmail, Twitter, Instagram, Facebook at Chem for Your Life. That's Chem, F-O-R, Your Life, to share your thoughts and ideas. And if you enjoy this podcast, you can subscribe on your favorite podcast app. And if you really like it, you can write a review on Apple Podcasts. That helps us to be able to share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. Jam Robinson is our producer, and we'd like to give a special thanks to V. Garza, who reviewed this episode.